Humans have always looked at the stars and wondered. The dream of time travel is a powerful one. Imagine witnessing the birth of pyramids or soaring through cities of tomorrow. This yearning to step outside our present moment is universal. The river of time flows relentlessly in one direction, or so it seems. But what if it doesn't have to? Scientists ponder the nature of time. Is time an absolute, unyielding cosmic law, or is it something more flexible? We build machines to conquer distance and explore space. Could we one day build a machine to navigate the currents of time itself? The allure of time travel lies in its promise of ultimate freedom. Freedom from the mistakes of the past. Freedom to explore the wonders of epochs long gone or yet to come. Think about it. You could meet your ancestors or see historical events firsthand. This desire to control our temporal destiny is a profound aspect of the human spirit. To understand time travel, we must first talk about Albert Einstein. His theories revolutionized how we see the universe. Einstein showed us that space and time are interwoven into a single, four-dimensional fabric called space-time. The faster you move through space, the slower you move through time. Astronauts on the International Space Station age slightly slower than people on Earth. Gravity warps space-time, making time run slower. Einstein's theories tell us that time travel into the future is possible. While Einstein opened the door to future-bound travel, what about the past? This is where things get much more speculative. One of the most famous theoretical concepts for past time travel is the wormhole. Imagine space-time as a rubber sheet. A wormhole would be like punching two holes in different parts of the sheet and connecting them with a tunnel. This tunnel could be a shortcut through space-time, linking distant points in space or different points in time. The idea of wormholes, also known as Einstein-Rosen bridges, emerged from the mathematics of general relativity. However, the kind of wormhole you'd need for time travel is very specific. It would need to be traversable. Most theoretical wormholes are incredibly unstable, collapsing in an instant or filled with lethal radiation. To keep a wormhole open and stable, you would need something truly exotic matter with negative mass energy density. We have no evidence that such matter exists or that it could be created or controlled, so while wormholes are mathematically plausible under certain conditions, their practical construction remains firmly in the realm of deep theory. Another speculative idea involves cosmic strings, hypothetical, incredibly thin, and unimaginably dense defects in the fabric of spacetime. If two such cosmic strings were to pass each other at very high speeds, or if one were to form a rapidly spinning loop, they could theoretically warp spacetime so intensely that they create closed, time-like curves. These are paths through spacetime that loop back on themselves, potentially allowing travel into the past. But cosmic strings themselves are purely hypothetical. Finding one, let alone manipulating it, is far beyond our current capabilities. Theoretical concepts like these push the boundaries of our understanding. They inspire both scientific inquiry and imaginative storytelling. The brilliant physicist Stephen Hawking also thought deeply about time travel. He was intrigued by the possibilities but skeptical about travel to the past. Hawking proposed the chronology protection conjecture, suggesting that the laws of physics might prevent time travel into the past to avoid paradoxes. Why would the universe protect its own history? Perhaps to avoid paradoxes like the grandfather paradox. Hawking believed that some yet unknown physical principle might step in, making building a time machine that goes to the past impossible. Hawking famously conducted an experiment to test for time travelers from the future. In 2009, he threw a party and sent out invitations after the party had already happened. If time travel to the past were possible and if future humans had mastered it, someone might show up. He waited. No one came. This doesn't definitively prove past time travel is impossible, but it raises questions. Despite his conjecture, Hawking acknowledged that our understanding is incomplete. He explored scenarios where quantum mechanics might play a role. The many-worlds interpretation of quantum theory could offer a way around paradoxes. If you travel to the past and change something, you might simply create a new branching timeline. In this new timeline, your actions have consequences, but the original timeline you came from remains untouched. This suggests that instead of one history, there could be an infinite number of parallel histories. But again, this is deep in the realm of theoretical physics. When we talk about traveling to the past, we inevitably encounter paradoxes. The most famous of these is the grandfather paradox. Imagine you build a time machine and travel back in time to when your grandfather was a young, unmarried man. For some reason, you cause an accident and he dies before meeting your grandmother. If your grandfather dies, then one of your parents is never born. If your parent is never born, then you are never born. But if you are never born, how could you have gone back in time to cause the accident in the first place? This creates a logical contradiction. This is one of the core reasons why many scientists are skeptical about the feasibility of past time travel. Or, if it is possible, they believe there must be mechanisms to prevent such paradoxes. Perhaps the timeline is self-correcting. Maybe something would always prevent you from succeeding in killing your grandfather. Some physicists propose that the laws of physics enforce consistency. This is sometimes called the Novikov self-consistency principle. It suggests that if you travel to the past, you can only do things that were already part of history. You cannot change the past because your actions in the past were always meant to happen. You become part of a pre-written script. Beyond the grandfather paradox, there's another fascinating puzzle, the bootstrap paradox. This paradox deals with objects that have no origin. Imagine a time traveler with a copy of Hamlet. He gives it to Shakespeare, who publishes it. Centuries later, the traveler finds it and takes it back. So, who wrote Hamlet? It's an endless loop with no starting point. This is the essence of the bootstrap paradox. Long before scientists formulated theories about space-time, humans were telling stories about time travel. H.G. Wells's The Time Machine, published in 1895, is a cornerstone of this genre. It captured the public imagination. Wells sent his unnamed time traveler far into the future. He witnessed the evolution of humanity into two distinct species, the gentle Eloi and the subterranean Morlocks. This wasn't just an adventure, it was a social commentary, a warning about the potential paths of human development. Wells's work set a precedent, showing that time travel stories could be more than just thrilling escapades. They could be vehicles for exploring profound questions about humanity's destiny, the consequences of our actions, and the nature of progress and decline. Before Wells, there were myths and legends. Rip Van Winkle slept for 20 years, a form of passive time travel into the future. But the time machine actively put the controls into human hands, or at least, into the hands of its protagonist. Fiction allows us to explore the what-ifs, without the constraints of real-world physics. What if you could witness the dinosaurs? What if you could meet historical figures? What if you could correct a past mistake? Authors and filmmakers have delved into these scenarios with great creativity. These narratives often serve as cautionary tales, highlighting the dangers of meddling with the past. The butterfly effect is a common trope, reflecting our understanding of complex systems where tiny initial variations can cascade into dramatically different outcomes. Time travel fiction becomes a laboratory, a place where we can experiment with the flow of history and ponder the ethical responsibilities that would come with such an extraordinary power. When we think of time travel in popular culture, certain images instantly spring to mind. For many, it's a sleek, gull-winged DeLorean sports car. Back to the Future made this vehicle an icon of temporal adventure. Dr. Emmett Brown's invention, powered by plutonium, or later a lightning strike or Mr. Fusion, took Marty McFly on thrilling and often perilous journeys. The films masterfully explored the grandfather paradox, Marty almost erasing his own existence, and the consequences of altering the past for personal gain. The charm of Back to the Future lies in its humor, its heart, and its relatable characters. It made the complex idea of time travel accessible and entertaining. The rules were relatively simple. Hit 88 miles per hour, have 1.21 gigawatts of power, and try not to interact too much with your past self. Across the Atlantic, another, even more enduring time traveler has captivated audiences for decades. The Doctor, from the British series Doctor Who, travels through time and space in a TARDIS. The TARDIS, famously disguised as a blue police box, is bigger on the inside. The Doctor's adventures range from historical encounters to far-future alien worlds. The show often explores the philosophical implications of time travel, emphasizing the Doctor's role as an observer and protector. Doctor Who introduces concepts like fixed points in time, events so crucial that they cannot be changed. Both the DeLorean and the TARDIS represent the enduring appeal of the time machine, symbols of adventure, escape, and endless possibilities. So, where do we stand today, in 2025, with actual time travel research? As we've seen, Travel to the future is, in principle, understood. Einstein's theories of relativity provide the roadmap. Time dilation due to high speeds or strong gravity is a real phenomenon. However, achieving significant leaps into the future requires technologies far beyond our current grasp. We can't build spacecraft that approach light speed. We can't safely get close enough to a black hole to experience its extreme time-bending effects. For now, these remain theoretical possibilities. Travel to the past is a much more challenging proposition. The theoretical avenues, like traversable wormholes or manipulations of cosmic strings, rely on concepts like exotic matter with negative mass energy. We have no observational evidence that such matter exists. Many physicists, like Stephen Hawking with his chronology protection conjecture, suspect that nature has built-in safeguards against paradox-inducing journeys into yesterday. Research continues, but it's largely theoretical, exploring the very limits of general relativity and quantum mechanics. Current research often focuses on understanding the fundamental nature of time itself. The journey of discovery is ongoing, and who knows what secrets the universe still holds about the true nature of time.